The screen is visible to all.
Yes, sir.
Is the screen visible? Okay. Shall we start? Okay, coming to the next type of problems on the Darcy-Weisbach equation and other concepts. Using those concepts, we are solving the problems. Next, we'll take the third problem, that is an oil of specific gravity 0.9 and viscosity 0.06 poise is flowing. So, if the viscosity is given in poise, you have to tell me whether it is kinematic viscosity or the dynamic viscosity. Okay, so that oil is flowing through a pipe of diameter 200 mm at a rate of 60 liter per second. 60 liter per second. Find the head lost due to friction. So due to friction means you have to recall the Darcy-Weisbach equation or the Chase's equation. So head loss due to friction is for a 500-meter length of pipe. So that we need to find out. And also find the power required to maintain this flow. So how much kilowatt or watt power is required to maintain the flow of 500-meter length with 60 liter per second discharge. So to maintain this, what power is required and what is the friction loss in the given pipe. So once you just observe here, the poise is given. This is nothing but the dynamic viscosity mu. Okay. If the Stokes is given, that we have to recall it as kinematic viscosity mu. Okay. So rho by mu will be the kinematic viscosity value, or I think reverse. So that is mu by rho. If you take the mu by rho value is mu. So that is the ratio of dynamic viscosity to the density of the given fluid. So here in this problem, the fluid given is the oil, not the water. So first thing you have to remove that water in our mind. So in this problem, oil is flowing in the pipe. For that, we need to find out what is the friction loss and the power required to maintain the flow rate. So here the unit of the viscosity is poise. So I can take it as dynamic viscosity mu 0.06 poise. And once you try to convert this into Newton second per meter square, we need to divide this poise value by 10. Okay, so poise value by 10 if you divide, I will get the unit of dynamic viscosity in Newton second per meter square. Or normally we say viscosity of oil is in Newton second per meter square. Next is, in the problem they have given diameter of the pipe. So they have given 200 mm. So if you take in SI units meters, it is 0.2 meters. Then they have given density of the oil. So density of the oil, if it is required, you can write it, or else it is without that density also you can solve the problem directly by using this viscosity and density, or else you can solve by kinematic viscosity also by taking the ratio of rho by mu. In the denominator, I can write it as nu value. Nu in the sense kinematic viscosity, not a new value. It is a kinematic viscosity value. That also we can use. So density, if you want to find out, I can write it as 0.9 into 1000. That will be 900 kg per meter cube. So these all things we have studied in the first chapter itself. From the first chapter, we are trying to convert these all units and write it in SI units. Next is, here discharge is given in liter per second. So our requirement, we need to convert that into meter cube per second. So recall the conversion. how to convert this liter per second into meter cube per second. So in that SI unit, I'll get 0.06 meter cube per second. That is the discharge from the pipe. Then they have given the length of the pipe, that is 500 meters. So whenever the length of the pipe is given without changing area, means we can apply either Darcy-Weisbach equation or the Chase's equation. Provided in the Chase's equation, they should give some constant values. Okay. So if the without constant values, if you want to try to solve, then we should know the other indirect related terms. So like if I recall the Chase's equation here, why we are not going for Chase's equation? Because see the Chase's equation formula, that is for velocity. From velocity with Chase's constant, square root of mi. So that square root of mi means these values are having some interrelations with the factors CF. Okay, so this constant is nothing but rho g by f dash. We don't know f dash. Then m value is what? M is given by here d by 4. So d by 4 m we can find out. HF we need to find out. Okay, so directly we cannot go by Chase's equation, and they are not asking the velocity also. Directly they are asking the friction loss or the head loss due to friction, and they are asking what is the power required to maintain the flow rate or to maintain the discharge. Only that they are finding. So we are not going for Chase's equation. That point should be clear. And the flow, what flow is taking place? The oil is flowing in the pipe, not the water. Now coming back to these steps. Okay, so first we can recall the Darcy-Weisbach equation, that is 4FL V square by 2GD. In that, if I just go through this equation directly, the HF. So to find the HF, 4FL V square by 2GD, you can recall. In that, what all things are known? So that we have to first recollect. So say for example, formula is known to us. So that formula is written here, 4FL V square by 2GD. So in this, diameter is given, G is constant, F is not known to us. So this F we need to find out. L is given in the problem, length of the pipe, that is 500 meters, V square. So velocity is also not known. So now from this, one can find out the coefficient of friction in other way also. Okay, so as we discussed in the derivation, if the velocity is given or if it is not given also, we can find the other terms. So which other terms are required here? You can just see. So in this problem, so one can go by using Reynolds number. So for the Reynolds number, we know that it is rho Vd by mu. So why I am going by Reynolds number? Because one should decide for coefficient of friction or the F value. I can use one of the equation which relates Reynolds number. So depending upon laminar flow or the turbulent flow, we have two equations. So depending upon that, I can use this value. And now, how to find out this velocity? Because in the Reynolds number, rho Vd by mu, if you go, mu is given, density we know for the oil, velocity is not known, diameter is given. So when velocity is not known, but you know the discharge, can anyone tell me what relation I can use to find the velocity using this discharge? You can comment in the chat box or you can unmute and tell me the procedure. How we can find out velocity using the discharge value. Yes, very good. By using V equal to Q by A or by recollecting the continuity equation. Okay, A1 V1 equal to Q1 or discharge equal to area into velocity. From that relation, one can find out the velocity. That is average velocity. So from that, they have found out velocity equal to discharge divided by area. So area of the pipe is what? Pi by 4 d square. So pi by 4, 0.2 square if you take, so just check the values. Then you can find out velocity. Here it is coming around 1.91 meter per second. So this is required for our Reynolds number. And why we are going by Reynolds number? Because In the main Darcy-Weisbach equation, we don't know head loss due to friction. We don't know coefficient of friction. Okay. So to find that coefficient of friction, now what I'm doing is I am using this help of Reynolds number and the coefficient of friction relations. So from theory, so say for example Reynolds number, how much you are getting here? It is around 5.7 into 10 raised to 4. 5.7 into 10 raised to 4. Yes. So if it is 10 raised to 4 means it is in turbulent flow, because values are more than 4000 also, and also the 10 raised to value, if you see, it is more than 3, 10 raised to 3, more than 10 raised to 3. So keeping this value, so 5.7 into 10 raised to 4, that indicates the flow is above 4000 value of Reynolds number. So it is a turbulent flow. Now go back to the theory part, what we discussed. From that we need to choose what equation can help us to find the coefficient of friction. Yes, here. So HF we know 4FL V square by 2TD. Here, once you find out this F value, then we can find out head loss due to friction. So for that, we discussed in theory part that if the Reynolds number is above 4000, okay, to 10 raised to 6 values, up to that, one can use this F value as, small f value as 0.079 by Re raised to 1 by 4 or Re raised to 0.25. If it is less than 2000 or 2300 in laminar flow, then one can use this value, that is F equal to 16 by Re. Is that clear? So these equations are very important to find the coefficient of friction. And without coefficient of friction, we cannot find out head loss due to friction. So I'll take this formula now. In the turbulent flow, F is given by the correlation 0.079 divided by Reynolds number raised to 1 by 4. The coefficient of friction F equal to 0.079 divided by 57,300 you can substitute, or 5.73 into 10 raised to 4 you can substitute, raised to 0.25. If you find out, you will get the coefficient of friction as 0.0051. So using this coefficient of friction F, now I can substitute in head loss due to friction HF formula, that is 4FL V square divided by 2GD. F is 0.0051, V is 1.91, square you have to take here, V square is there. Then length is 500 meters. So directly given in SI units, directly you can substitute. And check this HF value, is it coming around 9.48 meters of water? Then for the power required, you can remember the equation like specific weight of the liquid WQHF, or you can remember in other way, that is rho GQ into head loss due to friction. So using this equation, one can find out the wattage power required to maintain this discharge or to maintain this flow in the pipe. Okay, so when you know the flow rate, when you know the head loss due to friction, and if you know the density or specific weight, one can find out the power required in this form. So I'm going to multiply now. Density 900, gravitational acceleration 9.81, into discharge in meter cube per second 0.06 into head loss due to friction 9.48. So here divided by 1000 is taken for kilowatt. So minimum power from the pump, or the minimum power what is possible from the natural flow from the high head to low head, that power required is around 5.02. So minimum requirement is 5.02 kilowatt to maintain this discharge. If it is above this power, also you can maintain the more discharge. So minimum or required power, at least required power is what? 5.02 kilowatt. So I hope all of you understood the problem. So only extra thing here is to find the power to maintain the flow rate. Rest all is learnt in our theory. To find the head loss due to friction by Darcy-Weisbach equation you can find out. And for that, the coefficient of friction is not given in the problem. So we are going by using Reynolds number and coefficient of friction correlation depending upon that Reynolds number. That is very important in this problem. So on that basis of turbulence or the laminar flow, we are deciding what equation for the coefficient of friction can be used. So once the coefficient of friction is found out, then you can utilize that F value in the Darcy-Weisbach equation. And rest all values are given directly or indirectly in the given problem itself. Like velocity, it is given indirectly by mentioning the discharge or by diameter or the size of the pipe. Okay. Is the values are correct? Power and head loss due to friction. Okay, shall we proceed to the next part? Okay, next, until now we discussed about the major loss by considering only a single pipe with the same diameter without any change in direction or without any change in the uh, type of connections in the pipe. Now we'll discuss the minor losses. Okay. So in the minor losses, we have various type of connections, or it may be the pipe itself is changing the diameters, or it is having some bends in the flow. In such conditions, the losses in the head, we are going to name them as the minor losses. Okay. So how these minor losses are all integrated in different ways. So one is the sudden enlargement. So all of you can imagine a pipe is having the inlet diameter. Okay, it is having more diameter as the inlet flow. Once the flow continues, what will happen? The gradually or suddenly. So here the name itself indicates sudden enlargement. Now what happens? The diameter is going to suddenly increase in the step itself. In one step itself, the diameter of the pipe is going to increase at very large values. So such type of connection you can imagine, or it is whether it is there here, no. So that you can recall by this PDF, flow through pipes. So in this you can recall the type of connections. This PDF also have uploaded in the course material for the extra reading, or any details if it is not discussed in the class, any extra things with theory and other things if is required, you can just recall it. So here you can see sudden enlargement or the sudden change in the diameter. So here inlet flow is coming. So gradually or suddenly, what is happening here? Suddenly, if the flow diameter is increasing, then flow will also occupy the larger diameter pipe. Okay, and in this region, initially or after the turbulent flow is achieved, the eddies will be formed. Eddies means the small amount of fluid will be having some vacuum generated here, or it is going to have some uh, rotations of the particles or mixing of the particles at this stage. Because only in the laminar flow it may be possible that fluid particles will occupy the sudden enlargement of the diameter and it can flow. But in the high velocity of flows, what will happen? The flow will be gradually occupying. The liquid is going to gradually occupy the full diameter. It is not that as the pipe is having sudden enlargement, the flow is also occupying the same dimensions. Okay, that is not possible here. So taking this type of head loss due to sudden enlargement, again we can consider section 1 and 2, applying the Bernoulli's equation. So here in this PDF, they have given full derivation, full complete derivation, step by step they have given. But what I felt is, and in our syllabus also, the derivation of these minor losses are not there. But to understand how they derived by this equation, you can refer these steps. And directly after deriving that with the help of Bernoulli's equation, the sudden enlargement or the sudden expansion head loss is given by He equal to entry velocity square minus exit velocity square, or you can write it as V1 square at smaller diameter velocity square, velocity at the larger diameter square. So that is V1 square minus V2 square divided by 2G. So by using this formula, one can find out head loss at the sudden expansion. So that is denoted by He. So after deriving, they are shown here. He is given by V1 square minus V2 square by 2G. Okay. Next part is the sudden contraction. So here you can just see the difference, how the pipe dimensions are changing suddenly and how the flow dimensions is taking place inside the flow. There are two components. So pipe dimensions, if you see, larger diameter pipe is suddenly decreasing in the diameter and flow is taking place like a nozzle. Suddenly the diameter of the pipe is reduced. So what will happen? Automatically the velocity will be very high. But seeing this sketch, what is that sketch? The sudden expansion, if you see, the area of the pipe is going to enlarge. And if you see the flow direction, here direction of flow is very important. If the direction of flow is from left to right, then velocity will be go on decreasing because of the large area. But the flow in the same situation, if you take reverse, if the flow is taking place from 2 to 1, then what is happening? It is sudden contraction itself. So there in the sudden contraction, what is going to happen? The velocity is going to increase due to the less area or the less diameter of the outlet flow. And the flow phenomena, if you see, the flow of water at high speeds after achieving some high speed, the larger diameter of flow is going to gradually reduce. I'm talking about flow, not the pipe. The flow is gradually reducing by creating some gap here with some eddies or what. Then once it reaches this sudden decrease in the diameter, again it is flowing like a venturimeter here. you can recall the venturimeter phenomenon, where in between the sudden change in the diameter and after some length, it is going to have some minimum area of flow. Okay, so this minimum area of flow, we are calling it as vena contracta, as same in our venturimeter. So same name is recalled here. So this is the diameter of the flow, smallest diameter of the flow. This is the smallest diameter of the pipe. Both are different. So to name that vena contracta area of the cross section area, there we have taken one more cross section CC, and flow is taking from 1 to 2 with a sudden contraction. So in this case, we are going to rewrite or write the equation for head loss due to sudden contraction using this equation. To sudden contraction, either you can directly use, as you are in JAB, what you have used, 0.5 V2 square by 2G. So it is completely dependent on the exit velocity. So half of exit velocity square divided by 2G you can use. Or else, if you know that vena contracta area, or what you can recollect here is area of the flow at section CC. Here, at section CC, what is the area? That you can take it as AC. And velocity at that flow is CC. So like that you can take areas. And this CC value is nothing but the ratio of, see here it is given. What is that quotient of contract? Quotient of contract area is, or contracted area is, CC equal to area of that contraction, area of the flow I'm talking at CC, take the area of the flow contracted. How much it is contracted, that area we have to require, not the pipe area. So that AC divided by A2. A2 is what now? The pipe diameter. So that ratio, if you know, then I can recall that as a constant CC. Okay. So this CC value, if it is known, or if it is given in the problem, or if you can find out, then you can use theoretically V2 square by 2G into bracket 1 by CC minus 1. 1 by CC minus 1 square. So this also you can note down for the sudden contraction in the pipe. So I hope this experiment on minor losses is done by everyone at this point. All students have completed this minor loss in the lab. Okay, then it is fine. So same equations again we are recalling here. And later we'll discuss some problems with combined losses, major and minor losses, which you have not done in the lab. Okay, so in this PDF, they have recalled 1 by CC minus 1 whole square as K as a constant that you can recall, or you can just remember this equation 0.5 V2 square by 2G, which is very simple. That's clear. So next is entrance of the pipe. So this is also nothing but the flow from the stagnant point, or the flow which is stored in a big tank. That flow is flowing through a small opening in the tank, through a pipe. So that we are calling it as entrance to the pipe. So there also we are assuming the flow is taking place with respect to the sudden contraction itself. Why? Because the big tank we are assuming zero velocity, okay, with a big large area. From that, the flow is entering through a small opening of the pipe with a small diameter. So that also resembles similar to the sudden contraction in the pipe. So again the same formula, and to just represent it is the entrance of pipe, they have taken HI, because they already HI is taken here, sudden enlargement of the sudden expansion. So HI is represented for the entrance of the pipe as 0.5 V square by 2G. Now why they have not recorded it as V2 square? Because we cannot differentiate the velocity of the tank and velocity of the pipe. Because in the tank, initially we assume there was zero velocity, or it is negligible, very small velocity from the sump or the big tank, and whatever the velocity is flowing only in the pipe, because tank we cannot consider as a pipe as V1, so they are not considered as number. So without that number means the velocity which is flowing in the pipe itself. So that pipe is connected to any size or any shape or any dimension of the tank. So in such condition, we are just calling it as V square by 2G. So whenever this V square comes, you just remember it is a pipe velocity. Okay. So any sketch is given here, you will see in terms of a pipe. So here sketch is not given. You can just recall your Reynolds experiment in the lab, where one big tank is there. From that, through a small pipe, the flow is coming out, and from that experiment, we are finding the laminar and the turbulent flow. So in that experiment, you can recall this entrance of a pipe experiment. The next is exit of the pipe. So at the exit of the pipe, what is happening? The flow is coming and freely it is going outside. Okay, just the water is falling from the pipe outlet. In such conditions, if you want to find out the losses, so that outlet of pipe, you have considered as H0, and velocity of the pipe or the velocity of the flow inside the pipe, that is taken here, that is V square by 2G. Okay, so that is the sudden exit of the pipe. So here the flow is coming out of the pipe and directly in the free atmosphere it is flowing out. So in such case also, if it is required, you can use this equation, and when the water is freely moving outside the pipe, there also you can find out what is the losses present at the section of the outlet flow. The next is gradual contraction or enlargement of the pipe connection. If the pipe connection itself is gradually changing, not sudden change. Okay, the gradual change is nothing but according to the flow, the diameter of the pipe is also changing, or as the pipe area is changing, see here, as the pipe area is changing here, what is happening because of the sudden changes of the pipe sizes, but the flow is not occupying all those corners. So due to this, what will happen? There will be more losses. But if you design the pipe itself with these gradual changes, okay, I will design the pipe such that it resembles the flow dimensions like this, the curvilinear path. Then we are going to recall that concept as gradual or smooth changes in the diameter, okay, in contraction or in the enlargement positions. So in such condition, you can use this equation, head loss due to gradual changes, that is HL, as K into V1 minus V2 square, or V1 minus V2 whole square divided by 2G. Okay, so this K value should be given in the problem, or we have to find out from the changes in the areas, that is using the contraction coefficient, CC value. So from that also you can find out K value, or K value, the constant value will be given in the problem. And V1, V2 depends on the direction, because here I didn't tell you whether the equation is for contraction or enlargement. So if you take contraction, V1 is for the larger diameter pipe, okay, V2 is for the smaller diameter pipe. And if you take reverse, sudden enlargement, then V1 becomes small pipe velocity and V2 becomes the flow in larger diameter pipe, that is V2 whole square. So K into V1 minus V2 whole square divided by 2G into K. If you take, then one can find out for the gradual contraction or the enlargement, what is the head loss due to friction. So I think here gradual changes they are not given here. Entrance of the pipe, exit of the pipe, due to obstruction in the pipe. Okay, here it is not given. You can just remember these equations. The next is the bend. So as I told you, bend and elbow are two different entities. Bend is the same material of the pipe itself, or the same length of the pipe itself, is turned into some given directions, or it may be turned in 90 degrees or 40 degrees, okay, or the flow directions are maybe continuously changing also. In such conditions, we are using this head loss due to bends HB as K into V square by 2G. Okay, so bends they have given here. Uh, Head loss due to bend K into V square by 2G. So K is what? Coefficient of bend. So this we need to find out, or it is given in the problem. So if the K value is not given, in such case, this equation you can note down using the uh, coefficient of contraction. You can use this equation K equal to 1 by Cc minus 1 whole square. Okay, and how to find out this coefficient of contraction? As I told, you can find out by area of contraction divided by area of the pipe in which the flow is going to take place. So these things considering, you can find out the K value, the constant K value. Then next with other fittings, if any other fittings are given, so for a given fitting like pressure gauge or some uh, changes in the directions of the flow if it is there, in such conditions you can go by again using that K value for a given instrument or the device which is connected for the pipe, and velocity at that point V square divided by 2G. So these are the various equations already you have seen in the lab how to use, and some of the equations are added in this discussion. So these are the different various equations theoretically we are using to find the head loss due to friction in different connections in the pipe, which are combinedly called as minor losses. And if there is no such connections, or if there is no sudden change in the diameter or area of the pipe, then that type of continuous flow in the pipe with any changes or without any connections in the pipe, such flow or such losses in the flow, we are calling it as major loss in the pipe. So I hope that these equations are understood to everyone. Now we'll take some problems on minor loss as well as combined losses, and we'll try to finish off this flow through pipe today. So first problem we can see here. Yes, the rate of flow of water through a horizontal pipe. Okay, flow of water through a horizontal pipe is, so why the horizontal pipe is given, you have to tell me. Horizontal pipe is 0.25 meter cube per second. So discharge from that horizontal pipe is given, Q value is given. The pipe of diameter 200 mm is suddenly enlarged to a diameter of, how much is the diameter? To a diameter of, okay, we'll see, to a diameter of uh, pressure intensity in the smaller pipe is 11.772 Newton per centimeter square. Determine loss of head due to sudden enlargement. So you recall HE equation. So from this equation, you can find out what is head loss due to sudden enlargement. That we need to find out. Pressure intensity in the larger pipe, we need to find out because pressure intensity in the uh, smaller pipe is given. Larger pipe pressure intensity we need to find out. That is P2 value we need to find out. Power lost in the enlargement. So how much power is lost in the enlargement of the sudden enlargement. So these things should be found out. Now here diameter, I think by mistake I have not written. So taking this area, you find out the diameter. How much is the diameter? And the problem itself you mentioned, a pipe of diameter 200 mm is suddenly enlarged to a area of 0.12566. So in that you write A2 and tell me D2. So first all of you find out this area A1 and using this A2 as given value, find the diameter D2 and A2, because in the question by mistake I have not taken the diameter. So area 1 as per diameter of the small pipe 200 mm before sudden enlargement is area 1 0.03141 meter square. A2 or the area of the sudden enlargement pipe is 0.12566 meter square. From this one can find out diameter D2. Then pressure intensity at pipe 1, small pipe, is given 11.772 into 10 raised to 4 Newton per meter square. So after converting centimeter to meter square, you can write it as 11.772 into 10 raised to 4 Newton per meter square. Then from the equation of sudden expansion V1 square minus V2 square by 2g, we know that velocity value should be known to us. So to find that velocity, some relation is given here. What is those relations? That is, discharge is given, areas are known to us. So once the discharge area is known, one can find out the velocity at small pipe and the large pipe. So small pipe velocity is V1 and large pipe velocity is V2. So once the flow enters from small pipe to big pipe, velocity is going to reduce. That's why V1 is higher value, V2 will be lower value. What is the diameter D2 in this problem? Is anyone using calculator? Please check this diameter. How much you are getting? 0.399. Okay. So one can note down diameter D2 is given in the problem as 0.4 or 0.399, or you can write area is given in the problem A2. Okay, that area itself you can write it as question 0.12566 meter square. Okay, now we found out the loss due to sudden expansion, that is around 1.816 meters of water is lost. Okay, and next question is pressure intensity in the larger. Now here in the problem we found out the velocity V1, V2. Also we know P1 value, P2 is not known, and in the problem they have mentioned horizontal pipe. So the potential head Z1, Z2 is equal. You can cancel Z1, Z2 equation with the Bernoulli equation, and later you can find out this P2 value. Okay, so cancel Z1, Z2 in the Bernoulli equation. Then V1 square by 2g, V2 square by 2g, you substitute the values. P1 by rho g, P1 value is given, densities of water. Then other side, P2 by rho g is unknown. Rho g is given, P2 is unknown. So ultimately from that Bernoulli equation, after simplification you will get P2 by rho g as 13.21 meters of water. From this we can multiply that 13.21 meters. So this value 13.21 meters is got from velocity V1, V2 and P1 after substituting in the Bernoulli equation. So multiplying this 13.21 meters of water into rho g value to multiply, so P2 can be found out as 12.96 Newton per centimeter square, or in meters square if you want you can multiply with 10 raised to 4. 12.96 into 10 raised to 4 Newton per meter square. So again, power lost or power required to overcome this loss, I'm using again the same equation, specific weight Q into HL or head loss, or you can write it as rho G QHE by 1000. So here power lost, what they are asking, it is only for the enlargement, how much power is lost due to this flow. So only by using this sudden expansion head loss HE, I am finding the power loss, the small power lost in the flow due to sudden expansion, not due to head loss due to friction. If it is head loss due to friction, you substitute HF as in the earlier problem. But in this problem, it is head loss due to expansion, HE. So please substitute these values and check the answers. Are they matching with you? Okay, time is 12:45. We'll take a break now. Again, we'll come back at 1 p.m. and we'll discuss the answers and we'll go to the next problem. Point 4453 is the power lost. Point 4453. Yes, please check this answer. Power lost answer is coming 0.4453 kilowatt. Kilowatt or watt? Is it in watts? 0.4453. 4.45 watts. Okay. So without dividing by 1000, you are getting 4.453 watt. So all of you change this kilo. Okay. The answer is in 4.453 watts, not in kilowatts. Kilowatt is huge power loss. And because of the sudden expansion or connections in the pipe, losses will be less. But we don't know what is the total power loss. So at 1 p.m. we'll continue the class after that. The screen is visible now. So the last column P2 value is correct. If anyone has checked the P2 value, please mention. Here it is 12.96 Newton per centimeter square. Please confirm from the Bernoulli's equation whether the pressure at sudden enlargement diameter is 12.96 Newton per centimeter square. P2, is it correct? The value what I written there in the notes. Okay. Now next we'll see one more problem. I think this is the last problem. So carefully see the problem here. A horizontal pipe of diameter 500 mm is suddenly contracted to diameter 250 mm. So both the diameters are given. Find the areas. The pressure in larger and smaller pipe are, say, the pressure in larger pipe and smaller pipe. So which you have to consider 1 and 2. So here it is a sudden contraction, means the initial pipe is a larger pipe 500 mm. So that pressure I'll consider 13.734, and after sudden contraction the smaller pipe is having the pressure P2 11.772 Newton per centimeter square respectively. Find HC. So this HC is nothing but the head loss due to sudden contraction. And if CC value is given here, so CC, as I told you, area of contraction to the area of the given pipe. So that CC value is 0.62, coefficient of contraction. Also find the discharge of water. So here to tell the flow in the pipe is water, finally in the question they are asking, find the discharge. What type of discharge we need to find out, whether it is a oil or mercury or any fluid. Okay, so for that they have mentioned water. So now from the given problem, only it is a sudden contraction. Everyone can just convert area and use that CC value. If the coefficient of contraction is given, then you can use this equation. What is that? V2 square by 2G into bracket 1 by CC minus 1 in 1 whole square. So using this equation, now we are going to find out what is the head loss due to contraction, sudden contraction. If it is gradual contraction, CC value will not come into picture. But if it is sudden contraction, then this coefficient of contraction will come into picture. So we are going to use that equation, that is V2 square by 2G, or you can just write V square depending upon the contraction pipe or small pipe. V square by 2G or V2 square by 2G into bracket 1 by CC minus 1 whole square. Okay, so here one should find out what is this V2, because in the problem they have not mentioned velocity anywhere. Okay, and here in the problem, to find the velocity, area is known for the small pipe or the large pipe, but the discharge is not mentioned. So in such case, what we can do is, again we can go by Bernoulli's equation. So in the Bernoulli's equation, horizontal pipe is given, cancel that Z1 and Z2, V1, V2, in that V1, V2, okay, we are going to find out V2 value. V1 is not given in the problem, okay, and we want only the V2. So taking only for the small pipe also, sorry, only for the big pipe, okay, P1, P2 values are given as it is. P1, P2 values are given. So I think you can assume V1 in terms of V2 or V2 in terms of V1. You can write the results because we don't know both. We don't know V1 or V2. But from the Bernoulli's equation, we can get the relation. We are not getting the answer. We can get the relation between V1 and V2. So in that, here they are getting V1 as V2 by 4. V1 value is V2 by 4. Okay, so that value, if you found out from the Bernoulli's equation, let's see what happens. Just a minute. Okay, pipes. Yeah, depending upon CC value. CC, how much they have mentioned? In the problem, CC value is given as 0.62. Okay. So if it is 0.62, you substitute 1 by 0.62 into V2 square by 2G. 1 by 0.62 minus 1 whole square. So if you substitute like that, we can get the value of HC, or the formula for HC as 0.375. So in this bracket, whatever the value is there, that is 0.375 into V2 square by 2G. That you will get. So that is 0.375 V2 square by 2G. So here I don't know V1, V2. From HC we know this relation now for the given CC value. Now can anyone tell me how they found out the V2 value? Okay, I assume that I also don't know V2 value, but how they found out this V2 value when V1 is also not known? So check by any other method. Can you find out velocities? And also check the values until that A1, A2, whether the values are correct. And this from the Bernoulli's equation, whether this V1 equal to V2 by 4 is correct. Yes, can you tell me how to find V1 and V2? Any answers in the chat box? If you tell this answer, at this point the Bernoulli's equation is understood by that student, or I hope that everyone has understood the Bernoulli equation or continuity equation. In future, we will not take those equations. Yes, when V1 is known, yes, A1 V1 equal to A2 V2. Okay, A1 V1 equal to A2 V2. What we are going to do by this equation when both the values are not known? Yes, A1 A2 is known. Okay, V1 is not known, V2 is also not known. Yes, very good. One can substitute in place of V1 as V2 by 4. Okay, I can write it as A1 into V2 by 4 equal to A2 into V2. So that what I am doing is both side I am considering same velocity in the form, means in the sense I am considering velocity in the form of V2, or else what you can do is you can write V2 equal to V1 into 4. A1 V2 equal to A2 into V1 into 4. Now what is the next step? Or you tell me how much you are getting. How much is the value of V1 or V2? Please others also try the answer. From this, can you get the V1, V2? If you are getting this procedure also can work to find one of the velocities. V2 is V1 by 2. But here I am getting by Bernoulli's equation, or I can substitute the same value in Bernoulli's equation also. Here it is V2 by 4. V1 is V2 by 4 from the Bernoulli's equation. Or V2 is nothing but 4 into V1, not 2 into V1. V2 is 4 times V1. A2 is A1 by 2. Okay, then what is V1 value in the meter per second? If you are taking the same ratio as like areas, what about the velocities? You can solve this problem other than continuity equation also. Even in Bernoulli's equation, you can substitute V1 as V2 by 4. There also by Bernoulli's equation you can find out one of the velocity, and then you can find out V2 velocity. Or one of the student here it is telling, what she is telling is area 2 is half of area 1. Similarly, can we relate V2 as V1 by 2? Okay, you can relate, but tell me the answer. How much is velocity V1 or how much is the velocity V2 you are getting? If that is around this value, then your procedure is correct. Velocity at 2, we are getting around 5.467. 5.467 meter per second. From this, you can find out V1. Yes, others, those who are finding from the A1 V1 equal to A2 V2, or you can substitute in the Bernoulli equation. So in Bernoulli equation, if I substitute, so from the problem you can just see here what is P1 P2. So Bernoulli equation I will recall here P1 by rho g. So P1 is 13.374, sorry 734 Newton per centimeter square is given. You substitute in meter square. Newton per meter square you substitute. P1 by rho g. Okay, rho is water. Density of water is 1000 plus V1 square by 2g. So V1 is not given. What I'll do, I will take V1 as V side of the Bernoulli equation. V1 square by 2g, I am taking V2 by 4 whole square. Left side and right hand side Z2, I am cancelling because horizontal pipe is given. Z1, Z2 I will not consider in this entire problem. Okay, equal to right side what I'll do, I'll take P2. P2 is 11.772 into 10 raised to 4 Newton per meter square divided by rho g plus V2 square by 2g I'll write as it is. Okay, V2 square by 2g as it is plus head loss due to sudden contraction. So that you have to add on the right hand side. That I can take V2 square by 2g into bracket 1 by cc minus 1 whole square, or what I can do, I can write directly this V2 square by 2g plus 0.375 into V2 square divided by 2g. Now in the Bernoulli equation what I did, by replacing V1 term as V2 by 4, I have written the Bernoulli equation entirely left hand side or the right hand side in the V2 form. From that one can find out V2 value directly, or by A1 V1 equal to A2 V2 also you can try whether the velocity are you getting the same answer. So that V2 value is 5.467. Now if you take this value, one can find out discharge. So A2 V2 equal to discharge. So discharge is around 268.3 liter per second, or you can write it in meter cube per second in any unit. And from the head loss due to contraction, so that is also asked in the question here. Head loss due to contraction, HC is asked. That's why I'm adding this HC in the Bernoulli equation. So HC is 0.375 V2 square by 2g is coming around 0.57 meters. So apart from this, last one column is there on combined losses. If anyone confirms this velocity is correct or any other value HC or Q is correct, then we'll proceed to the last problem. All other students should try this problem. V2 is 2 by 4. V2 raised to 2 by 4.
So it's just squared.
Square, eh?
V2 square by 4, sir.
V2 square by 4. Okay, then how much you are getting velocity? But from the continuity equation, if you check, it is around V1 is V2 by 4. By taking that, or you can, what you can do, one more procedure is, you can take A1 V1 equal to A2 A2. In that area, you can take pi by 4 D2 square, pi by 4 D1 square. Like that, you can substitute. Okay, in terms of diameter, because in the problem they have not mentioned area. I think area we have found out later. Diameters you can take. Yes, here A1 A2, what you know, or else what you can do, pi by 4 D square, pi by 4 D2 square. From that also you can take the velocity relation. So I may get around V1 as, I can write it as 0.25 by 0.5 whole square into V2. So in that condition, it is coming V1 as V2 by 4. What about others? Only 2-3 students are replying. Okay, today will you try it once again later? You try it writing in detail. So whatever the answers and short procedure I have mentioned here, this continuity equation or Bernoulli's equation, you write in detail and later check that whether this V1 how to be substituted in terms of V2 and other things, and these answers, head loss due to contraction, velocity at sudden contraction pipe, or velocity at the uh, larger pipe, and discharge. Is that okay? Sir, if you substitute V1 equal to V2 by 4 in continuity equation, then V2 gets cancelled. Okay, then go by Bernoulli's equation. In the Bernoulli's equation, because it is having addition sign, from that you can check. Then I think you can find by Bernoulli's equation one of the velocity that you can substitute in continuity equation to find the other velocity, or directly by this V1 equal to V2 by 4. From that also you can find out one of the velocity. Okay, please try it later. We'll check the answers in next class. The last problem I'll discuss now. V2 is 6.469. Okay. .469. Any others? See, this 6.464 is from Bernoulli's equation. Much. Okay, then find the V1 velocity, or else check that H and other things from Bernoulli's equation. Okay. Then what about these values? H, C, Q, and all things will change. So I think take this problem. All of you should tell me the answers in the next class, because only few are replying, few are trying the solutions. Maybe that answer may be correct. 6.4 what you are telling, this may be also correct. Okay. So I think everyone should solve this problem and tell me the answers in the next class. Okay, I'll take the last problem and we'll stop the class today. This last problem is a horizontal pipe. So again, Z1, Z2 is cancelled here. 40 meters long. A pipe is 40 meters long. Is connected to a water tank. Now here, see, earlier problems we have mentioned only diameters, not the length, because it was having only contraction or sudden expansion or some fittings in the pipe. But in this problem, once they have mentioned the length means, you have to go back to the Darcy-Weisbach equation, because it is having the head loss due to friction due to this length, 40 meters long, is connected to a water tank at one end and discharged freely into atmosphere at the other end. So this pipe is connected to a tank, a big tank is connected. From that, the water is flowing to the small pipe, okay, which is horizontal pipe. In that, the pipe is 40 meters long. It is connected to a water tank on the left side, you can assume. And from the tank, through the pipe, the water is coming out and discharged outside. Okay, at the one end. And other side, it is discharged freely into the atmosphere. At the other end, on the right side. Left side tank is there, right side, it is kept open. Like that pipe is there of 40 meters long. For first 25 meters, yeah, now the condition starts. For first 25 meters of its length from the tank, the pipe is 150 mm diameter. From the tank from the connection of the tank from left side to the right side 25 meters length, the pipe diameter is 150 mm size and its diameter is suddenly enlarged. After exactly 25 meters, the pipe is suddenly enlarged to 300 mm diameter. So it is a sudden expansion condition in the pipe. From the tank to the pipe, it is sudden contraction. So there are two conditions. And at the exit, the water is directly kept open to the atmosphere. The height of the water level in the tank is 8 meters above the center of the pipe. Okay, above the center of the pipe, the water level maintained in the tank is 8 meters height. Considering all losses of head which occurs, determine the discharge from the pipe, taking the coefficient of friction F for the Darcy-Weisbach equation as 0.01 for both sections of pipe. So in both the pipes of 300 mm and 150 mm diameter pipes, the coefficient of friction is 0.01. Now question comes, the sudden enlargement of 300 mm diameter, it is up to what length? So what length? It may be up to 300 mm. So that we can find out by taking total length of the pipe for 40 mm, 40 minus 25 mm. If you take, you will get the length of pipe with sudden enlargement. Okay, so 25 meter, it is having diameter, smaller diameter 150 mm. Okay, another 15 meters, it is having 300 mm. So taking this concept by applying the Bernoulli's equation, okay, Bernoulli's equation is applied at any two sections. So as we are starting from the tank here, from the left to right side, always, what we are doing here, from the tank we are taking the P1 by rho g plus V1 square by 2g plus Z1 equal to right side forms. So here generally what I have written, Bernoulli's equation at the tank and to the outside side, considering second velocity plus all other losses you have to add. Okay, now first is for the given length or for the Darcy-Weisbach equation for the given length of 25 meters or the 15 meters, that is divided from the 40 meter long. Here I am applying the Darcy-Weisbach equation for the pipe 1 and pipe 2 with two different diameters. That is Darcy-Weisbach equation is considered. Sudden contraction of the pipe or at the inlet side, that we have considered 0.5 V1 square by 2G. So that is mentioned in this theory point, this equation. Sudden contraction or pipe connected to a tank, that is 0.5 V2 square by 2G. Then next is sudden expansion, that is V1 minus V2 by whole square by 2G. That is one part. Then again, the head loss due to friction in the next pipe, next 15 meters length, 4 Fm2 V2 square by 2 Gb2. So like this, we are considering all these losses on the other side, and we are writing the equations from the Bernoulli equation. And from the continuity equation, as the diameter of two pipes are mentioned here, okay, that is D1 and D2 is mentioned for the pipes. From that, we can find out this V1 V2 relation or the V1 V2 value. So that is coming around V1 is 4 times V2. So this we are going to substitute in the entire Bernoulli equation. This is what I am asking in the earlier problem. If you substitute this value in the entire Bernoulli equation, what is the velocity? So similarly, we have taken here all the terms they have substituted in terms of V2. Okay. So take the Bernoulli equation from the tank to exit of the pipe. If you consider, and after simplification with pressure value is given the problem. See the problem, pressure values are not given. So after simplification, they are getting around with considering the velocity values. 8 equal to V2 square by 2G, and also the losses they have considered. Sudden expansion, sudden contraction, all those losses they have considered with the losses in the pipe. So that is 8 equal to V2 square by 2G plus 8 V2 square by 2G plus 106.6 V2 square by 2G plus 9 V2 square by 2G plus 2 V2 square by 2G. Then from the question, what we need to find out is discharge. The only discharge we need to find out. So all of you note down the steps. Is the connection is there or no? Okay. Yes, please note down the detail this procedure. So from the continuity equation, as I told, V1 can be written as A2 into V2 divided by A1, taking on the one side. I can take pi by 4 D2 square into V2 divided by pi by 4 D1 square. So considering that pi by 4 D square, V1 we can write it as 4 times V2, what is mentioned in the right hand side in this solution. Next, taking this value, okay, in the Darcy-Weisbach equation. What I'll do now, as I know the V2 value, I'll substitute in the second Darcy-Weisbach equation, that is HF2. HF2 I'll substitute 4 into 0.01 into 15 meters, because L2 length is 15 meters. 15 meters into V2 square by 2G. Okay, so from that we can get around 2V2 square by 2G. So that is mentioned here. Second pipe 2V2 square by 2G, it is from the HF2 relation. Then HF1. So here HF1, what you can do? L1 is 25 meters. F is 0.01, same value. V1 I'll write it as 4V2 square. Sorry, 4V2 whole square. So 4V2 whole square, if you take, divided by 2G into D. So D2 is given. D2 is 300 mm. So once you substitute that value, I will get HF1 value. So once this HF1, HF2 values are known, you can add them with the Bernoulli's equation and you can substitute to get the velocity. So V2 is coming around 1.11 meter per second. And discharge is A2 into E2. We are getting around discharge value 70.078 meter cube per second. Or if any changes are there, you can just find out and tell me. So only thing in only these two problems, what I did is I've taken all short forms so that you can analyze in the Bernoulli equation and continuity equation, and you only substitute and tell me the answers. Okay, so take your own time, discuss all these points, and in the coming to the next class, we'll check the once again what procedure you have followed and what results you have found out. Okay, and we'll recorrect those answers. If they are wrong, we'll recorrect, or if it's correct, we'll continue. And from the next class, I think Wednesday. So Wednesday we'll start with the next chapter, that is a dimensional analysis in the 4th unit. That chapter will start in the next class. Okay. So let's stop here. Okay.